All right, before I discuss a specific problem, I'd like to discuss the overall big picture. So this is what AP Central called, when they were asked, what is the problem? It's an example of what you're going to do to us. This is the example of the 25-minute problem they chose. Okay, so I'm going to go through it, and I'll walk you through the pieces, and I want to explain the general of our architecture. All right, so here's AP Central's version of what you're going to do. The exam date is May 14th. Oh, I should scroll that in so you can see it. Oops, okay, May 14th. Since we're on Pacific time, it's 1 p.m. You'll be given 25 minutes to respond to the first question and 15 minutes to respond to the second one, 5 minutes in between to take pictures, and 5 minutes for the second one to take a second picture. Now, let's talk about quantitative quality. The first question will be quantitative qualitative. It's going to be 60% of your grade and 25 minutes long. What does that mean? I described this before in class. I just said this is an argument between two students, typically. The other thing it's always part of, and this is what they really are trying to get at, is they try to get you to say words and then back it with equations or numbers. Okay? Now, some thoughts. One, why pick this question? Well, you pick this question because you know, okay, you know that they are going to want to be able to type an answer. In physics, that's not a common thing to be able to do. But if you read this next question, it almost always could be typed, right? There's almost nothing in there that revolves numbers and things. So that's probably why they chose this question. And the second one is because they really like this question. It's not a bad question. On the grand scheme of the 5 questions they could ask, it's certainly better than the paragraph argument, which is the next thing we're going to have to deal with. And that one's terrible. But we will do this one. For qualitative, quantitative, I want you to crush this, okay? All right, and by the way, this is a hugely hard example. Let's go back to it. All right, hopefully you've tried this problem before. A reminder, don't argue with the question. Okay, first year when these things went out, my kids, this person basically said, the reason why electrons flow through a wire is because that is downhill for electrons. And from the paragraph response, it sounded like the person actually meant it was downhill. And so my students said, so the question was, explain in what ways this student was right. And the student was not right. The student's wrong, right? And so all my students jumped on that, he is wrong. No, the question was, explain in what ways was he right. So you're going to choose the answer, okay, he's right because, and then finish that sentence, okay? All right, so I'm going to give you some examples of things going forward. Take a look-see as these go. Okay, so this is a disc. It's sliding along there. It hits the stick, and the stick has a pivot. This is me throwing a tennis ball at the door problem, right? So there shouldn't be that shocking. Okay, so it says here, the left of the rod is a rotational inertia I is attached to frictionless horizontal surface by a frictionless pivot as shown above. Point C is this midpoint of the rod. The rod is initially motionless, but is free to rotate around pivot A. So it's a door with a really well-greased hinge, right? And there's no door stops, no nothing in the way. If I hit it, the door is going to swing open. Agreed? All right. The student will take a slide disc of mass m disc towards the rod with a velocity v naught, perpendicular to the rod, and the rod, when it strikes the rod, a distance x from the pivot. The student who wants the rod disc system to end up with as much angular speed as possible. So he wants to slam it so the door starts moving. Okay? Actually, no. Yes. He wants to make as much angular speed as possible. Okay. So he wants the door to start moving. He wants the disc to go with it, which is kind of interesting or whatever. All right. Okay. Suppose the rod is much more massive than the disc. Okay. So the rod, it's a door, and I'm throwing a little ping pong ball at it. To give the rod a much greater angular speed as possible, should the student make the disc hit the rod on the left of point C or the right of point C or at point C? Okay, so the answer to the question is, well, remember, you have 2 ways to look at this. One way you could say, well, angular momentum of a object traveling in a straight line, remember, is LVR. MVR here, MVR. Mass, velocity, radius. Now we use that specifically with satellites, but it still works, as I said, with tennis balls being thrown at the door. The radius refers to how far you are from the pivot point. So the farther from the pivot point, the bigger this gets, because M and V are not going to change. So one thing to say is you get greater angular momentum if you're to the right rather than the left of C. That's one answer. Check. They give that to you. Second choice for an answer. All right, well, torque. Where is this disc going to apply a force? If I apply a force here, it has less torque than if I apply a force here, right? The farther you are from the pivot point, the stronger you are, like a wrench, right? So you'd say, hey, the farther from the pivot point, the stronger I am. Therefore, because I have greater torque, okay? Which one of those is the correct answer? The guys, both are correct. Either one would give you the 1 point they're giving for this problem. You also want to say to the right of C, make sure you check this box. Otherwise, they give you no points and laugh at you for not trying the problem. Okay, I'm going to pause it so I can get the next piece. All right, so here comes the crazy bad physics. What does this student do? He goes on the internet. He finds a formula. That's a formula. Does it work? The answer is we're suspicious because it came from the internet. Aren't we? Please say you're suspicious because it came from the internet. And so we look at this problem and go, all right, so here's my equation, m disk x v naught. And it says, regardless of whether the equation for angular speed is correct. So in other words, I don't care if it's correct. Tell me if it agrees with your qualitative reasoning in part A. In other words, does it make sense with part A? Back to part A. Part A says, if you go to the right, you get faster speed. So the bigger the x, the faster the speed. So you look at the equation and you're like, well, yeah, see, x is right in the equation. The bigger the x, the faster the speed. Indeed, it does, right? The bigger the x. Now notice, I didn't talk about physics. I did what they said. The bigger the x, the faster the angular momentum. Right? The faster the angular speed, my bad, faster the angular speed. Okay. And that's true in equation and in part A. All right. Feeling suspiciously light on physics? Yeah. Here we go. Let's do that. Another student deriving an equation for both collisions. He comes up with his own equation. Good for him. The rod makes a mistake. The rod makes a mistake and comes up with. So it says he made a mistake. They tell me he makes a mistake, which is nice of them. And omega equals ix v naught m disk over d to the fourth power without deriving the correct equation. Still haven't asked you to do physics, right? Can I find the correct equation? I could find the correct. No, we don't want to find the correct equation. And that would be hard to find the correct equation, but at least it's something we should be able to do. It says, without finding the correct equation, can you tell that this equation is not plausible? In other words, does not make sense. So you're supposed to look at the problem and go, well, what doesn't make sense? A number of things don't make sense. For example, right away, look at the mask of the disc on the bottom. The bigger the mask, the slower the door moves. No. The bigger the mask, the faster that door moves. So that doesn't work, right? What about d to the fourth? D is the length of the door. Why would it be to the fourth power? It makes no sense at all. Why would that be important, right? But the big one is, frankly, the mass and the disc on the bottom. I think that is the one you should be looking at for realsies. And then you could say is, look, the I on the top, which is inertia, that should be stopping the door from moving, right? Because inertia is how hard it is to turn something. So the bigger the inertia, the faster the door goes. No, it's supposed to be stopping it, so it should be the slower the thing goes. So I is in the wrong place, mass of the disc is in the wrong place. And either one of those would get you, let's read the points, 3 points. Okay? So, that's all good. All right? All right. Now, if you check units, which would be a reasonable thing to do, it turns out they set it up so the units work, and good luck with sorting your way through that one. All right, let's get the next piece. All right, so the next question at hand is this. Okay? Immediately before colliding with the rod, the disk rotation inertia around the pivot point is mass of the disk x squared. Now, again, you should kind of know that, right? Because that's the mass distance from the pivot point squared is how you find inertia. Barely covered that, but look, they gave it to you, right? It's not like you had to know that. Its angular momentum with respect to is mvr. Okay, that's ridiculous. We knew that, right? What are you doing with us here? Its angular momentum is mvr. Okay, fine. Derive the equation for the post-collisional angular speed of the rod. Okay, so when you have a collision, what are you thinking? You should be thinking momentum. Since the thing is turning, you should be thinking angular momentum. So you're going to go momentum before because momentum after. Technically, because this is a... I can't find my pen. Nice, I found my pen. Oh, my pen's right down there. Okay, where's my pen? Wow, no luck with my pen at all. My thing's frozen. All right. Hello, pen right, somewhere, right. All right, I'm going to write with this. Oh boy, this is going to be fun. Writing with a, no. Okay, well, I give up on that. Okay, so it says momentum before equals momentum after. I do apologize. I'm now officially writing with a pen. Good luck with that. I cannot write with a pen. I'm writing with a mouse. Okay, so LB. I'm using L because angular. Do you use momentum before equals momentum after? I assume they give it to you, right? If you use P, right? Probably shouldn't do that, but that's okay. So this is M V naught X. That's momentum before it hits the door, right? Afterwards, it's going to, the two are going to stick together. So you're going to have inertia of the door, which is a big I, right? You're going to have plus, it told you the inertia of the disk is mx squared, so I'm just going to add that in, times angular speed, all right? And so then all you have to do is what? Right? You're going to, or we asked for angular speed, right? Angular speed, omega. So I'm going to take this, plunk it down here, and that would be my final answer. Right? No problems there. Shouldn't be that awful. A little weirded out by the answer key. It doesn't even, look, the answer key doesn't even care if you get the right answer. The answer key just wants to know, do you realize that when you have two inertias, you have to add those up? Do you recognize what it's a momentum before it's momentum after problem? All right, fine, give it to them. Give them all the points. All right, fair enough. That's nice of them. All right, let's move forward. Let's see if I can get the last one in an appropriate amount of time. Here we go. Oh, I want to pause it so I get some. All right, so consider the collision when the equation part D derived now, except now that suppose the disk bounces backwards off the rod instead of sticking to the rod. The post-collision angular speed of the rod, the distance bound to be greater than, less than, or equal to. Okay, so we just got to ask the question momentum before equals momentum after again, right? Momentum before equals momentum after. Oh, good, my pen's back. Okay, so momentum before was mvx equals, I've got myself the door, which is going to be I omega, plus I've got now, I've got a negative mvx. Now this v is not the same, right? So I'm going to say v naught and v nu or something. But here's the important part. Look at this equation. This is going to be a negative value, right? Because it was going one way, now it's going the other way. So if it's going the other way, then when I move to the other side, this is going to make a bigger number, right? Which means my omega has to be bigger than it was before. All right, it has to be greater than. Okay, so after the balancing collision, it has to impart more momentum because the disk went from going this way to going this way. So its angular momentum went from one way to the other way, which means the door is going to go. If it sticks, then it's just, then it doesn't impart the going the other way right part. Okay, you think about it like a cart going along a track, it hits something and bounces off. Things are going to go faster because, again, over here, you're going to have negative mv. So not only does the cart stop it, but it also has to push it the other way, which means this thing gets more of an impulse, which makes it go that way. All right, that should be it.